Welcome back to the Symphonics series on building a Bacnet stack. In today's episode, we're starting with a quick look at how Bacnet device discovery actually happens. Using YABE to send a WHOIS request and Wireshark to capture the IM responses on the network. From there, we'll break down these two essential Bacnet services, WHOIS and IM, and then walk through how to implement them inside our custom BACnetIP stack. Let's get started. So here's the idea. At the APDU layer, every Bacnet message begins with a PDU type. This single byte tells us instantly what kind of operation the device is performing. Whether it's sending a request, replying with data, confirming an action, or reporting an error. And in total, Bacnet defines 8 different APDU types. Let's walk through them quickly. First, we have confirmed request. This is used for services that expect a response, like read property or write property. Next is unconfirmed request, which does not require any reply. Classic examples are WHOIS and IM. Then we have simple ACK, which is just a straightforward acknowledgement. After that is complex ACK, which is similar but includes additional data. For example, when returning a property value. Moving on, there's segment ACK, used when a message is split into multiple segments. Then comes error, sent whenever a confirmed service fails. Next is reject, used when the device cannot handle the APDU at all. And finally, abort, which stops a transaction when something goes wrong, such as a timeout or internal issue. Once you recognize these APDU types, reading Bacnet packets, especially in Wireshark, becomes a lot easier. In Bacnet, a confirmed request is a message that always requires a response. It uses an invoke ID to match each request with its corresponding reply. And it supports segmentation for larger messages. The APDU also includes options like whether the message is segmented, whether the receiver accepts segmented responses, the maximum APDU size, and how many segments are allowed. Confirmed requests are used by several key Bacnet services, including confirmed read property, write property, and read range. They're also used for subscribe COV, acknowledge alarm, and file operations like atomic read file and atomic write file. These are the services you'll see most often when working with BACnetIP. Unconfirmed requests in Bacnet are simple messages. There's no invoke ID and no acknowledgement is expected. They're often multicast or broadcast, keeping the overhead small and communication fast. These messages are commonly used for device discovery and lightweight notifications. Common unconfirmed services include IM, I have, unconfirmed COV notification, WHOIS, who has, UTC time synchronization, and write group. These are the services you'll see most often on a Bacnet network. A simple ACK has no payload. It only indicates that the request was processed successfully. It includes the invoke ID and the service choice, so the device knows which request this acknowledgement belongs to. Simple ACKs are typically returned for operations like write property, where only a success or failure response is needed. A complex ACK can contain segmented data, allowing large responses to be sent in multiple pieces. It uses the invoke ID to match the reply with the original request. Typical use cases include read property multiple, read range, atomic read file, and responses to device communication control requests. A segment ACK is used only when segmentation is enabled. It acknowledges the receipt of a specific segment number and can request retransmission if a segment is missing. It can also indicate that more segments are expected, ensuring that large APDUs are transmitted safely and reliably. An error is sent when a confirmed service request was understood. but could not be executed due to a Bacnet error. It includes an error class and an error code, and still uses the invoke ID to match the original request. Sending an error indicates that the request was syntactically correct, but something prevented it from being processed. Common examples include unknown object, unknown property, write access denied, value out of range, and invalid tag. A reject indicates a protocol violation. The request is not processed at the application level, and there's no service-specific error returned. This usually happens because the APDU structure is malformed. Common reasons include an incorrect invoke ID, an invalid PDU type, an incorrect number of arguments, or a length mismatch. And finally, an abort APDU ends a transaction after it has already started. It indicates a failure mid-transaction and can be sent by either the client or the server. It may include a reason code to explain why the transaction was stopped. Typical reasons include timeout, segmentation not supported, buffer overflow, unexpected sequence number, or the application itself aborting the transaction. Alright, now let's get to the most important part: Bacnet services. This is where all the communication happens. From alarms and events, objects and devices, to file operations and time synchronization. Understanding these services is key if you want to build or troubleshoot smart building automation. So basically, there are two main types of Bacnet service. First, confirmed services. These are the ones that need a reply from the device you're talking to. Second, unconfirmed services. These don't expect any reply, so they're kinda one way. Which services you actually need depends on your device profile and what BIBs, that's Bacnet, interoperability building blocks, your device supports. But no matter what, every Bacnet device has to implement a few basic services. Who is IAM for discovering devices on the network. Read property to read object properties. Write property to change properties, but only if the device allows writing. These are the core services in the Bacnet-based device profile, the must-have stuff. In Bacnet, devices are split into two roles: clients and servers. Clients start the conversation by sending requests, and servers just handle those requests and reply. In this video, we're diving into the server side only. Why? Because trying to build both client and server at the same time gets messy. It's tricky to test and debug. The client part? We'll cover that in another video series. Next up, let's dive into the WHOIS and IAM services. These are all about device discovery. Think of it like saying, "Hey, who's out there?" That's WHOIS. Any Bacnet device on the network that hears this will reply with IAM, telling you who it is, its device ID, and some basic info. So basically, with WHOIS and IAM, your system can find all the devices on the network automatically. Super handy when you're setting up or managing a Bacnet network. Alright, the WHOIS APDU is really simple. First, there's the PDU type. This tells the network that it's an unconfirmed request. Next, we have the service choice, which shows that this message is a WHOIS. And optionally, you can include a device instance range, so that only devices within that range will respond. Now, we're diving into our BACnetIP stack, looking at the function BACnetAPDU receive handler. So what does it do? Basically, it receives an APDU from the network, figures out the PDU type, and sends it to the right handler. Here's the flow. First, we grab the PDU type, the upper nibble of the first byte. Then we do a switch case. Maybe it's a confirmed service request, an unconfirmed service request, or one of the other types like simple ACK, complex ACK, error. There are 8 in total. Okay, we're focusing on unconfirmed service requests, because that's where WHOIS lives. In handle unconfirmed service request, we first check the service choice, the next byte in the APDU. If it's WHOIS, we call handle WHOIS. If it's IAM or something else, we call the matching handler. Here's how our Bacnet device handles a WHOIS request. The handler starts by decoding the optional low and high device instance limits using the function WHOIS decode request. This function reads up to 2 unsigned integers from the APDU. If they're present, great. If not, both limits stay at -1, meaning no filter. After decoding, we just check whether our device instance falls within that range. No range? Then we respond by default. Range present? We only respond if we match. If we should respond, we build an IAM message and fill in the required fields. Device object type, our instance number, max APDU size, segmentation setting, vendor ID. Right now these values are hard-coded for testing, just to make it easy to verify the WHOIS right pointing arrow IAM flow. Later, you can move them into a device configuration structure or a header file so everything becomes clean and customizable. So the flow is really simple. Decode limits right pointing arrow check instance right pointing arrow send IAM when appropriate. That's the core of Bacnet device discovery. Alright, let's break down the Bacnet IAM APDU. This is the message a device sends to announce itself on the network. The IAM is part of the unconfirmed service request category. Every APDU starts with an APDU type, which tells the receiver what kind of message it is. For IAM, the APDU type is unconfirmed service request, and right after that, there's the service choice, which indicates exactly which service this message represents. In this case, IAM. Inside the APDU payload, we pack all the key information other devices need. Device identity, which combines the object type, always device, and the device instance number so every device on the network can uniquely identify us. Maximum APDU size we can accept, so clients know how large their messages can be. Segmentation capability, like whether we support segmented transfer or not. Vendor ID, showing who made or owns the device stack. So basically, the IAM APDU is a device's business card on the network. The APDU type tells other devices, this is an unconfirmed request, the service choice says. Specifically, this is IAM, and the payload gives all the details needed to communicate with the device. This message is compact, simple, and essential. Without it, Bacnet devices wouldn't be able to discover each other or know who's out there on the network. Alright, let's go back to our Bacnet stack and see how we actually send an IAM response. This is handled by the function Bacnet IAM send response. Its job is simple. Once we decide to respond to a WHOIS, it encodes the IAM APDU and sends it out to the requesting device. First, we prepare a small buffer for the APDU. Then we call IAM encode response. This is where the APDU is actually built. Step by step. PDU type and service choice. We start by setting the APDU type to unconfirmed service request and the service choice to IAM, so the network knows what kind of message this is. Object identifier. We encode the device object type and instance number, basically telling the network, this is who I am. Maximum APDU size. We encode how big a message this device can accept. Segmentation supported. We indicate whether the device can handle segmented transfers. Vendor ID. We encode the manufacturer or vendor identifier. All of these fields are encoded in a Bacnet application layer format. which ensures that every device on the network can correctly decode them. We'll go much deeper into the application layer encoding in the upcoming videos. So don't worry if it seems a bit abstract right now. Once the APDU is ready, we call Bacnet APDU transmit, which prepends the NPDU header, handles the addressing, and actually sends the packet to the destination device. Finally, the function returns the length of the APDU sent, so we know how much data went out. So in short, this function is the bridge between our device information and the network. It takes the whois request and turns it into a proper IAM announcement that other Bacnet devices can read and respond to. We start by building the project in Kyle and running the debugger on the device. Next, we open PowerShell and send a quick ping to make sure the device is alive. Alright, check this out. When we hit scan in YABE, boom! It instantly finds our device. There it is. Device 12345 right on the network. Everything's coming together. And you can actually see our device alive on the network. We click on our device in YABE. Device 12345. But YABE reports could not fetch object. In Wireshark, we see that YABE sent a read property service request to our device. Since we haven't implemented that service yet, there's no response, which is why YABE shows the error. And that's exactly what we'll tackle next. Implementing the read property service so the device can respond properly. See you in the next video.